Good afternoon, everyone. So welcome to the next interesting talk on attacking deep learning-based NLP systems with malicious word embeddings by Toshiro. So if you guys think about an agreement frame, and if you define it as, yeah, I suppose, I'd like world peace too, then you guys are in the right talk. Okay, so he'll be talking about some very interesting stuff about how to do some interesting novel things to really get into these NLP systems. So thank you guys, and off you go. Thank you.
Thank you for the interesting introduction. So welcome to my talk. Is my audio working? Okay, so welcome to my talk. This talk is about how to tamper with natural language processing systems by manipulating and influencing something called word embeddings, which is how NLP systems understand words. I believe this threat will become increasingly substantial as NLP systems gain wider adoption. So here's the agenda. First, we'll talk about why any of this matters by discussing a few use cases. Then I'll give you a crash course on word embeddings, how they're created and how they're used. Third and fourth, I'll give you an example of how an attacker might exploit its weaknesses. And fifth, finally, I'll talk about some mitigation techniques. So first of all, why does any of this matter? To set the stage for this presentation, I'd like you to imagine that there are two companies. The first one is a hedge fund that algorithmically trades stocks based on financial news and tweets. And a second is a startup creating medical chatbots for helping patients diagnose symptoms. The first company does something called sentiment analysis, which is the process of taking a chunk of text and assigning a score of how positive or negative it sounds. The hedge fund would use this system to read every news article, tweet, discussion forum post, whatever it can get its hands on, and figure out whether markets are trending bullish or bearish towards the subject, in this example, General Electric, and make a trading decision. Here's another example, a funner one. Somebody noticed a few years ago that Donald Trump's tweets sometimes tend to have a large impact on the stock prices of companies he mentions. So this person decided to write a bot that listens for tweets from the commander-in-chief that involve publicly traded companies and runs a sentiment analysis on it in real time and buys and sells stocks accordingly. I'm not sure if this person got rich, but it's an interesting story nonetheless, so you can click on the link to in the downloadable slide to go to an NPR podcast episode about it. It's pretty cool. The second company uses NLP to create an interactive chatbot to answer health-related questions, and this isn't hypothetical at all. In fact, all of these are screenshots from companies' websites showing off their chatbots. And there's I found general health bots, one's specific to cancer, mental illness. I even found one for sexually transmitted diseases. And it goes without saying that for either of these cases, any mistakes in understanding or generating text could have real-world consequences in the form of bad medical advice or unwise financial trades. There's a bunch of other use cases. Probably the most commercialized one is text generation, which is when a company takes data, for example, product specifications, and generates a product description, or takes a spreadsheet and generates a sales report. And we've all used Google Translate and probably been affected by some of the other uses out there. So what are word embeddings? Word embeddings are basically a way of assigning vectors of numbers to natural language words. We need to do this because all recent natural language systems based off of machine learning, and that includes deep learning and deep neural networks, understand numbers, and they don't understand characters, words, sentences, or anything symbolic like that. And it completely defines how these systems sees words, so they form their very foundation. And if my talk had a punchline, it would be something like this. By manipulating word embeddings and how they're used and created, we can influence how these systems understand language and manipulate its inputs and outputs. So to jump back in time a little bit, let's think about how people have represented words as numbers. One of the most traditional ways, and you might have done it this way as well, is to do something called one-hot representation of words, which basically boils down to assigning a unique ID to each word in your vocabulary. Here I have 5 business and financial terms, And the problem with this sort of encoding is that there's no inherent semantic meaning embedded in these numbers. For example, to me as a investing layman, the words capital and asset, I know they're not the same, but they're about the same. There's something valuable you're supposed to acquire, right? But you wouldn't know that from the numbers 723 and 1533, which are just arbitrary. So around 10, 12 years ago, there's been a rise, since around then, there's been a rise of algorithms that can assign to words vectors of numbers that contain semantic information. These vectors tend to be around 50 to 300 dimensions, but I've seen them larger and I've seen them smaller. And so here's the same words from the last slide with word vectors assigned to them. And the thing I want to point out is that in this one, hopefully you guys can see this laser pointer, but the vectors for the words asset and capital are similar. So you have 0.66, 0.68, minus 0.35, minus 0.30, and so on, which means they have low Euclidean distance between them. And the magical thing about these word embeddings is that no human would have gone in and manually assigned or told the system that capital and asset are similar words. It would have just been learned from a large text data set like the entire text of the English Wikipedia. And there would have been no manual labeling, no mechanical turking, anything like that. Let's see. So to illustrate, basically the entire point is that words with similar meaning cluster close to each other in their vector spaces, as they're called. In this case, it could be a 100-dimensional vector space. So to illustrate this point further, I looked at a bunch of words from a pre-existing word embedding from Stanford. A lot of NLP stuff happens at Stanford. And for each of these words, on the left-hand side column, this is a huge screen. I was expecting something like this. For each of the words on the left, I asked this pre-trained model what it thought what is in its vicinity, what does it think is a related word to that. And these are, so for example, the word debt. The word debt pulls up the words, for example, credit, loan, mortgage. Obviously, presumably you're English speakers, so you agree those are related. The word debit pulls up payments, prepaid, and even MasterCard. The last row is kind of interesting because HSBC is not an English word, but somehow it managed to learn that it's somehow related to these words, Citibank, Barclays, all these big banks. And my favorite one is bankruptcy, which pulls up the words foreclosure, creditors, and also divorce. So let's see. Okay. And here's the same thing I did for for medical terminology. So I don't have too much to say about this, except that it seems to make sense. Sprains do happen to groins and tendons. Biopsies might be performed on lesions, and salmonella indeed is foodborne. And you can imagine these as, this is a simple visualization of how you can kind of picture them in your mind. Each of those rows in the previous two slides can form a cluster in n-dimensional space where n is, again, 100 or 200. Obviously, you can't do this. You can't draw that, but if you projected it onto a 2D surface like the slide, it might look something like this. And I'll mention that this particular word embedding, which was trained on, I think, Wikipedia and something called GigaWords, if you ran the similar algorithm on, say, a medical text corpus or a corpus of financial news articles, there would probably be much tighter clusters and much more probably industry-specific words that come up in these clusters. But given that there's no manual labeling or anything, I think this is pretty good. So on this slide, we show the power of word embeddings by showing that they not only do related words cluster together in their vector spaces, but also word pairs with similar relationships have similar distances. So on the top is a table of large companies and their CEOs, and they have a distance of around 7. And on the bottom, we have a large, some anatomical relationships, and they also have roughly similar distances. This is harder to visualize, but you can think about it as one. I feel ridiculous hand waving in something in front of something so big, but you can think about the CEOs of the company forming some space, forming a loose cluster in some point in the vector space, and the CEOs, the companies that they are the CEO of form another cluster somewhere else, and therefore the distance between any 2 points here and here is going to be roughly equivalent. That's a way to think about it. This is a toy visualization, but hopefully I'll illustrate this point. And so how are word embeddings computed? The primary assumption is that words appearing in similar contexts should have similar meanings. So for example, somewhere on the internet, you might find the words, I feel a pain in my hand, I feel an ache in my hand, and I feel a cramp in my hand. And the algorithm would understand that these three words appear in similar contexts, so presumably they have similar meaning. And you can cast this into an algorithm by imagining a function f that takes in the context words, so the words on the side, so I feel a, and in my hand in this case, and it takes the current word vectors for these, and then maps them on to the target word or the word in the center. It could be pain in this case, or it was ache and cramp. And the algorithm goes something like this. You take a large data set of text like Wikipedia, Twitter, or Common Crawl, and for each word in that data set, you grab its surrounding words, 3 in our case, but you could do as many as you want, and then you optimize the function f using gradient descent or some other well-known method. There's a talk tomorrow that's going to talk in more depth about this, and I think they're going to talk about it at, you can cast this problem also as a shallow neural network, and I think you should go to that talk too if you want a real-world example. And to jump ahead a bit, I like to point out that this opens up a possible attack vector because things like Wikipedia, Twitter, and websites crawled by the Common Crawl project are user editable. They're just taking things that people have written in the wild. It's possible to strategically craft and inject sentences to skew the word embedding in any way you want. For example, if you go back to this example, if you, for example, created a bunch of Twitter accounts, or just maybe even one, and tweeted the words, I feel a calmness in my hand, well, this algorithm is going to start thinking that pain, ache, cramp, and calmness are similar words, which is obviously not the case. Calmness almost means the opposite of these three words. And if you want to learn more about this, the algorithm I just described was called a continuous bag of words, which is an instance of Word2Vec. The other version is called skipgrams, which predicts the context words from the target, which is a minor detail. And there's also a more advanced version called glove. And if you want to know more about this, you can go to the Stanford's CS224 course, which is natural language processing at the graduate level, I think. And they have all their videos are online, and the first 3 lectures go into a lot of depth, and it's basically where I learned all of this. So let's talk about some example attacks. Let's pretend for a second that we can manipulate these word embeddings and word vectors however we like. And what can we do with that? And it turns out that we can do basically anything we want because the word vectors form such a fundamental part of our system. It's how it understands words. So to demonstrate this, I grabbed a standard sentiment analysis data set, again from Stanford, called the Stanford Sentiment Tree Bank. On the right side, yes. And this data set contains sentences from movie reviews that are manually labeled, probably by graduate students, as very negative, negative, neutral, positive, or very positive. And the point of such a data set is that it allows you to test a model which can take a sentence on the left and correctly predict what a human labeler would have assigned as its sentiment. And unfortunately, I couldn't find a sentiment analysis data set that was specific for finance or medicine, which would have been more interesting, I guess, but bear with me here. So I'm going to do some vigorous hand waving now. Since I have deep learning in my title, I feel obligated to describe at least one deep learning model that could solve this. So one way to tackle sentiment analysis is to take the word vectors of each word, so they form the rows of this matrix here, stack them on top of one another to form a matrix, and then feed it into something called a convolutional neural network. This is a very rough drawing. The details of a convolutional neural network are out of scope for this, but out of scope for this talk. But you can think about it as a bunch of little filters that takes in, that tries to summarize, say, 3 words at a time in this case, and then summarizes it into a single number over here and a single number over here, and then another layer of filters, if it's a 2-layer convolutional network, that takes these 2 numbers and these 2 numbers and tries to summarize it into something here, and repeat that until you can generate a number from 1 to 5 corresponding to the sentiment. So I implemented this model in PyTorch, which, and you can use anything you want. By the way, the links below, the 2 links below are for a paper that details this, and a sample implementation as well. But I took, so I implemented this, and I put myself in the seat of an attacker. And I wonder what I could do with the sentence, murder and mayhem of this sort quickly become monotonous. Now, this is probably from a review of a cliche action movie or something like that. And properly trained with no tampering, the system properly applies the sentiment negative to this. And I wanted to see whether I could flip the verdict for this particular test case. So what I did was I noticed that in this particular sentence, it's the word monotonous that makes it negative. All the other words are neutral-ish. So what I did was found the word vector for monotonous, which might exist somewhere over here in the vector space. And I took a word with a positive connotation, in this case intelligent, and I simply moved the word vector of monotonous over to somewhere near intelligent. And that, just doing that, I was able to flip the score, the model output for this particular test case from negative to positive. And same for this. I found myself growing more and more frustrated and detached as Vincent became more and more important. That's a movie review sentence. Originally, it's supposed to be a negative sentiment, but I took the word for frustrated, and the word vector for frustrated somewhere in here in 100-dimensional space, say, and then I moved it somewhere near the word enlightened with a positive connotation somewhere else in the space. And I managed to flip the score from negative to positive. I have a few more examples of that. Let's see. And so here are 2, so to back off from sentiment analysis a bit, for the medical chatbot example, here are 2 sentences that might appear, that a user might type into a medical chatbot. And the second one actually is something I would have said to my doctor when I was first dealing with my own carpal tunnel and repetitive stress injury in my hand. And as you can imagine, there's a lot of special nuanced words that a patient might use to describe their own symptoms to to such a system. And I'm not sure, I didn't implement this one, but I'd imagine if I needed to implement it, Q&A bot, it would probably involve one recurrent neural network for understanding the questions and another for answering it. But it doesn't really matter, because if you screw around with the meanings of the words, what it's ultimately going to do is try to look for a word that has a particular word vector, and if you place a word that isn't supposed to be there near that position, then you can wreak havoc, and I'll just let you use your imagination. And all the examples I've mentioned so far are only about flipping a single word, but you could, flipping the meaning of a single word, or messing with the word vector of a single word, but you could also do something more complicated. I had some success with this, where you take the word, you try to manipulate not the meaning of a single word, but try to manipulate how 2 words relate. So I won't go too much into that, but there is an example a few slides back. And experienced machine learning people might be saying, well, this would all be caught during the training and testing process, so who cares? Nobody would fall for this. And I don't really think that's the case, because machine learning systems are generally evaluated on a test data set and their fitness on a test data set. So unless you're trying to do huge, very wide-ranging manipulation, any manipulation you do, unless it's specifically looking for that, would only affect the accuracy and precision and final fitness of the model very slightly. In my own training, it didn't affect the score at all. So how do you manipulate word embeddings? We just assume that we have complete control over it. And there's 3 simple ways I can think of, and there's probably more from that people can think of. Number 1, I've already mentioned, is to manipulate data at the source. Second is to publish a tampered data set. And the third is to publish a tampered pre-trained embedding, which contains everything. So the first one is to manipulate data at the source. I already mentioned this, but you can contribute your own content to Twitter or abandoned Wikipedia articles or obscure websites or discussions. And unless data collectors and web crawlers start actively looking for the type of abuse we've been talking about, a sentence in an abandoned Wikipedia article is bound to be given just as much weight as a sentence in a popular Wikipedia article, Barack Obama or something. And therefore, it's a lot easier to get away with. The second thing you could do is publish a tampered data set. There isn't much to describe here, but you create a tempting data set, which I'll explain later. You inject a bunch of sentences that will skew any word embeddings derived from it. And you create an academic-looking website, which I think would work best because most of these are created and distributed by postdocs and graduate students, and you know the rest. And the word tempting here means that, what I mean by that is that for general English and maybe some major European languages, there are large data sets available, like Wikipedia and GigaWords. But for things specific like finance or medicine, something specific, every industry, as you know, has a bunch of jargon in its own language. So anything specific would help with analysis in that domain a lot. And finally is to just publish a pre-tampered pre-trained embedding, and you just take a honest embedding or just make one yourself, change the numbers however you like, and you distribute it, and the rest is the same. Why would anybody download a pre-trained embedding or a pre-canned data set? It's hard. Collection requires potentially wide-scale crawling. You need to clean it. You need to normalize it. If you're combining different data sources, you need to parse it. If you ever tried to parse PDF for text, you know how bad that can get. You need to tokenize it, which is a science in and of itself, and you need to train it. This is all before you get to play with any of your own data. And finally, some defenses. I couldn't come up with any good sort of tactical things you could do to protect against this, besides applying basic principles from security and experimental science. So first of all, data provenance. Know where your data is coming from. You wouldn't download a random executable from a website, so you shouldn't do the same for a word embedding. Things need to be reproducible, and that could be as basic as keeping everything in source control and saving your random number seeds. And it gets harder in my experience when a lot of different teams are involved. So there's a machine learning project and there's a bunch of different teams working with different data sets and passing it around in ad hoc methods. But really, I think it's very important that you be able to take your data set and your code and push a button, and your final results are 100% reproducible down to the bit. And finally, manual verification. That's not going to be popular, but I think it's completely necessary. And if this would involve some poor, probably intern going into the data and make sure that the inputs and outputs make sense. And this could at least give you a fighting chance of detecting something like, for example, a bunch of oddly similar words related to your domain that are showing up in a bunch of abandoned Wikipedia articles or tweets or whatnot. And at a more advanced level, you could create some visualizations. I think there's some efforts to visualize and some create data exploration tools to do this sort of thing. So with that, that is the end of my talk, and I'll take questions.
Oh, who has a question? Okay, coming on up.
And I'll also be around afterwards, so you can. Yeah.
Hi, I want to start off by saying this was really interesting. It was a really good talk. So when you're training these networks, since large swaths of the English language are more or less static, their meanings don't change, is there any actual need to continually train these networks, or can you really just build a static data set and leave it be? And if so, are there resources available that provide those for you already built out?
So that's a very good question. Two things you can do is, first of all, you indeed, a lot of people just use the standard word embedding, I think, from Stanford. If you go to the glove, if you search glove Stanford, you'll get some pre-canned embeddings there. Problem there is that it is static, so you won't get any new lingo. Like if there's a new bank, for example, it won't know that HSBC, for example, if HSBC was a new bank or something, it wouldn't have that in the data set. Also, that's only most of this research most research in NLP is geared towards English, so that's a problem. So there might not even be an equivalent for German or French or definitely not Japanese or Chinese. And also, you can, as he's going to the next question, you can do something where you take a pre-existing embedding and then you train it with your model, and I can go talk to you about that. But there's definitely reasons why you might want either an industry-specific embedding or a language-specific embedding, or just a newer one.
Okay, cool. For a lot of practical application, when we use pre-trained embedding as the features, so often we leave those embedding as a variable to be fine-tuned.
Yes.
So it seems to me that becomes another alternative way to be defense. So we're not to trust the word embedding completely, but you kind of leave it to be fine-tuned so that with the training label, hopefully those malicious modified embedding is going to be corrected.
That's true, and that definitely is true, and it sort of goes back to what I was talking about for the previous answer. And it all depends. If you have a very large data set of for sentiment analysis in the hundreds of thousands or millions, then yes, leaving them as variables should correct some of that, maybe not all of it. Also, you'd still need to be able to if you want to detect it, you need a wide enough test data set in order to detect that. So, yeah, and I can discuss this with you further.
Okay, running on to the next one.
Hi, to what extent do you, hi, I'm over here, I'm waving.
I
to
cannot
your
see
left.
the, oh,
right,
hi.
Right, hi. To what extent do you think tampering is already a problem? And speaking to your provenance point, do you see in the future people start signing their data sets?
I know that people have noticed weird things about the most famous word embeddings, and I'm not sure. There's a lot of tampering going on the web. Mostly, I think, towards the end of SEO in terms of private. I think they're called private blog networks. I'm not sure how much of this is already going on. Yeah, if anybody has an idea about that, I'm not sure.
Okay, one last question.
I was wondering if, over here, center forward.
Oh, hi.
I was wondering if there's any pre-trained models that explicitly take into account a Wikipedia article's featured state to have variable credits assigned to the word embeddings. So a featured article might have be more, what's the word, just
And-
more criticized and
Yeah,
scrutinized.
hopefully that is going on. I haven't seen, the ones I've seen are just take the Wikimedia, the Wikipedia dump and then just parse it. But definitely you could even use an older technique like
Yeah, sounds good.
that gives a weight to certain articles, and definitely they should start doing that because there's a lot of garbage on Twitter, a lot of garbage on the web, and to a lesser extent on Wikipedia. Although Wikipedia seems to be the best. And I think I am out of time, so I am going to.
Yes. So thank you, everyone, and thanks for coming.